This video is created by Anuj Mondal. Section 1. Introduction. The fiery birth of a unique coal. Jhama is a special heat-altered form of coal found across Indian coal fields, often called natural coke or natural burnt coal. It forms by in situ thermal metamorphism, intense natural heating underground. Not a man-made furnace process, but a geological phenomenon. Heat source 1. Igneous intrusions, magma invading or nearing coal seams. Heat source 2. Long-burning mine fires. Intrusions bake surrounding coal for millennia, altering chemistry and structure. Seam fires ignite via oxidation or human activity and smolder for decades. Both processes drive off volatiles, leaving a denser, carbon-rich mass. Caking and swelling properties are lost. It cannot make prime metallurgical coke. Major occurrences: the Damodar Valley coalfields, notably Jharia, Raniganj, and Bokaro. Visually, Jhama is dull, hard and compact, often grey-black. Unlike shiny banded bituminous coal, its luster is subdued and uniform. It feels dense and massive, sometimes appearing compact, or vesicular, pores formed by violent escape of gases during superheating. Many voids are refilled by secondary minerals like carbonates and silica. Proximate analysis. Moisture around 3%. Volatile matter typically below 10%. Ash content commonly 24 to 40%. Fixed carbon enriched, often 60 to 70%. Elementally, about 63% carbon, with hydrogen, nitrogen and sulfur around 1 to 2%. Vitrinite reflectance is markedly elevated. This confirms thermal maturity and explains loss of coking ability. Jhama is classified by degree of thermal alteration. Slightly altered, partially devolatilized, may retain some plasticity. Moderately altered, dense, dull, fully non-caking. Completely altered, a natural coke analog, highly porous and strongly consolidated. Industrially, it is termed a special low-volatile natural coke. Low-volatile fuels suit processes needing steady heat with minimal flame. Mosaic textures signal strong carbonization at high temperature. Flow textures show alignment from semi-fluid movement. Granular or vitreous textures indicate intermediate heating. Fibrous textures reflect directional heating near intrusions. SEM reveals pore networks and microcracks. These features predict strength, grindability, and permeability. Section 4. Reserves and distribution. Mapping India's natural coke. Globally significant, but estimates are tricky due to irregular deposits. In India, Jharia is the epicenter of Jhama resources. Surveys estimate about 5,313 million tons. About 39% from intrusions, 61% from seam fires. Raniganj and Bokaro also host substantial Jhama. Deposits are lens-shaped, patchy, and discontinuous. Hard to map. Boreholes provide thickness and depth control. Resistivity and seismic detect anomalies between cores, integrated with surface mapping and historic mining data. A denser grid raises time and cost. Geological complexity remains a major hurdle. Section 5. Industrial applications. Putting Jhama to work. Despite limits, its high fixed carbon and low volatiles are valuable. It acts as an effective reductant and steady heat source. As a minor blend in metallurgical coke production, typically 5 to 10% in the charge blend, mixed with prime and medium coking coals for economy. Extends scarce coking coals with minimal impact on coke quality. In iron ore sintering, Jhama can partly replace coke breeze. Low volatility supports a steady combustion front and adequate heat. Trials report good performance and cost benefits. Pulverized coal injection. Fine coal into the tuyeries for heat and reduction. Reduces expensive metallurgical coke demand. Gasification converts Jhama to syngas for power, chemicals, or fuels. High temperatures and ash handling make it a strong candidate feedstock. Section 6. Challenges and constraints. High ash, often over 30%, lowers calorific value. More fuel is needed, and ash waste volumes rise. Abrasive minerals increase wear on mills, boilers, and handling gear. Expect higher maintenance and downtime. Conventional washing yields marginal ash reduction. Minerals are too fine and intimate. Thermal alteration destroys softening, swelling, and fusing behavior. Therefore, Jhama cannot serve as primary coke for blast furnaces. Use modest blending ratios to avoid weakening final coke. Lean toward finely ground uses like PCI. Consider gasification, briquetting, or agglomeration as required. These steps add cost. Apply selectively where value returns. Section 7. Conclusion. Jhama is natural coke formed by magma intrusions or underground fires. Volatiles are stripped, leaving hard, porous, carbon-rich material with high ash. It occurs in immense quantities in India's Damodar Valley, especially Jharia. It cannot replace prime coking coal on its own in steelmaking. The path forward: thorough characterization, strategic blending, targeted beneficiation, and advanced applications. PCI converts Jhama from a problem into a high-value injectant. Gasification unlocks energy and chemical value despite high ash. Match material to process. Don't force ill-suited uses. With smart engineering, Jhama becomes a national asset for metallurgy and energy, turning a natural challenge into a sustainable, strategic resource.